Okay, so section 2.1, we're going to start with something called a mathematical system, and then we're going to get to direct proofs and counterexamples. And then in the following sections, 2.2 and so on, we're going to go over more kinds of proofs. So first of all, what is a mathematical system? Well, it's another word for things that you've already seen before in your other math classes. It's simply a collection of axioms, definitions, and undefined terms. And we'll go over what each of these things means in just a second, if you're not familiar with them. So in a mathematical system, axioms are what you assume to be true. So for example, in geometry, one of the axioms is that there is exactly one line between any two distinct points. And you might know other axioms from things like algebra or numbers. Let me just write out that axiom. There is exactly one line between any two distinct points. Okay, so like I said, these are things that you're assuming to be true. You might know some other axioms. And we'll talk about more axioms later. This is just one example. Definitions are what are used to create new concepts from your old ones. So for example, you can define what it means to be a right triangle, sticking with geometry. And if you don't remember, a triangle is a right triangle if one of its angles measures 90 degrees. So you're creating the idea of a right triangle from a few old ideas. You would need the idea of what a triangle is in general, a polygon with three sides. And you would also need to know already what angles are. And you put those two ideas together to create the idea of a right triangle, which you're probably familiar with from geometry, Pythagorean theorem, and all sorts of things. Trigonometry, even. Okay, so the last thing, probably the part that was unfamiliar, is the idea of an undefined term. So in any mathematical system, there are going to be certain terms that you don't give a definition. They're just going to be something that is implicitly defined by your axioms. So they're understood by context and not by definition. So continuing with geometry, we don't define what a point is or what a line is. So those are some examples from geometry, points and lines. I'm going to say Euclidean geometry here. It's not really important. What I mean by Euclidean, it refers to the kind of geometry that you learned in high school. But there are other kinds, so I have to be specific. Okay, so that's the basic idea. You have things that you're assuming to be true. You put your old ideas together from your axioms to make new definitions. And sometimes there are terms that you don't define, like points and lines in geometry. And you might remember that we didn't really define what a set was when we were talking about set theory. That's usually an undefined term. Okay. And in your mathematical system, you have these ideas, these axioms, definitions, and undefined terms. And what you want to do, usually, is to use logic to create theorems. So a theorem is a proposition that has been proved to be true in your mathematical system using logic. So an example of a theorem that you might have seen back in geometry about triangles is this one. If two sides of a triangle are equal, then the opposite angles to those two sides are also equals. So just to draw a little demonstration, if I can, by hand. So if I draw two sides that are equal, and then complete it with a third side. So maybe I'll write the same letter, A, to show that these two sides are equal. And then the third side could be something else, maybe B. Then what this theorem says is that the sides opposite the two equal sides, so let's label them. They're equal, so they would get the same label, let's say theta. Okay. And then this could be something else, like phi. Okay. So if this doesn't seem super familiar, or if geometry was one of those challenging subjects back in high school, we're not going to focus too much on geometry when we're proving things. It's just a good example for some of these terms that we're talking about at the beginning of class today. Okay. And I also need to talk about two other kinds of theorems. Sometimes you don't call a theorem, you don't use the word. Sometimes you'll use these other words, like a lemma, L-E-M-M-A. And lemmas are used to prove other theorems. So they're usually simple or not very important by themselves. But they're useful to prove more important things, and they get called lemmas. Maybe I'll use the word uninteresting by themselves. Another kind of theorem is called a corollary. And corollaries are theorems that follow easily from another theorem. So you don't have to work very hard to prove them. So you'll see both of these words, and they both mean a theorem, but a different kind of theorem. So they're going to be propositions that have been proven to be true, but lemmas are used for other things to prove other theorems, and then corollaries are easy theorems, let's say. Okay, before I flip over to the next page, are there any questions about these new definitions and words that we're talking about today? Okay, so William is asking if I have any good examples of lemmas and corollaries, and let's see. Maybe I'll get to some on the next page, or at least maybe one of those two. So what I want to do next is to look at two different mathematical systems, and then look at some examples of axioms, definitions, and theorems in these systems. So for example, Euclidean geometry is the one that we've been talking about so far. And there are other axioms. I'm not going to list out all of them. So we talked about the one, let's see, I can just flip back. We talked about the axiom that says that there's exactly one line between any two distinct points. Another one of the important axioms in geometry is this one. Given a line and a point not on the line, then we can create a parallel line. And in fact, this axiom says there is exactly one parallel line. Parallel to the original line and through the given point. So this is a very wordy axiom, and the wordiness is the reason why I'm not going to try to write all of them for you guys. But in drawing terms, let's say, in picture terms, if I'm given a line and then some other point that's not on the line, then what this axiom is telling us is that we can always create exactly one line parallel to the original. Maybe I'll make it dashed. Parallel to the original and through my point. So this axiom is a wordy way to say something that's kind of pictorially, obviously true. And we can also talk about some other axioms from the real numbers, and I'll only mention a couple of them again. For example, there are axioms that say that multiplication is commutative, meaning I can do it in any order. And the way you would write that is this. For any real numbers x and y, x times y is equal to y times x. And this is called commutativity. Or the commutative property. Here's another axiom. This one says there is a real number which we usually use the symbol 0 for. Where we can add 0 to any other number and get the same number back. For any real number that we like. So if you add 0 to a number, you don't do anything. That's one of the axioms. Okay, so all of those axioms should be familiar. There are also some familiar definitions in both of these systems. And maybe I won't write out the whole definitions, but you know, there's definitions for things like a triangle, okay, so 3 line segments that are connected. There's some other things like supplementary angles. That one I might want to actually write out. 2 angles are supplementary. If their measures sum up to 180 degrees. Okay. So there's lots of other definitions, squares, rectangles, octagons. All of these words have their own definitions. Okay. And then back over in real numbers, we also have all sorts of definitions. Can just write down a couple. Maybe I'll just mention the words. Things like positive numbers. You would need to define what those are. You probably know what the definition is, the numbers that are greater than 0. And then there's, negative numbers, numbers that are less than 0. And there's other ideas like absolute value. And I'm not going to write out the definitions for these since you guys already know them. Okay, and this list, both of these lists really, could just continue on for quite a ways. There's all sorts of definitions that you probably already know even. Okay, so those are the systems themselves. What we're going to be talking about more than just the simple definitions are theorems. And we can write down maybe just one example in each, just to get an idea of what they look like. So I already wrote down one theorem from Euclidean geometry that says that if 2 sides of a triangle are equal, then their angles, their opposite angles, are also equal. So maybe instead of a theorem, I can, let's see if I can find something that we would call a corollary or something. So here's an example that your book calls a corollary. If a triangle is equilateral, then it is also equiangular. And this is actually a corollary of the theorem on the other side of, or on the first page, excuse me. So if a triangle is equilateral, which means that all of its sides have the same length, then it is equiangular, meaning all of its angles have the same measure. So like I said, this is a corollary to the other theorem because it would be easy to prove this one was true if you knew the other theorem already. We won't prove it right now, but we could. So maybe let's talk about some other theorems in real numbers. You can write them symbolically, like this one, that says for all x in the real numbers, x times 0 is equal to 0. So this is a theorem that you could prove. So what I wanted to point out with this theorem is that sometimes theorems are written out symbolically, like this one, instead of in words, like the ones that we've talked about so far. Here's another theorem. Okay. And this is one that I should use the word lemma for, since someone was asking earlier what a lemma might look like. This one says, if n is a positive integer, then n minus 1 is also a positive integer. So for example, if you start with 5 and subtract 1, you get to 4. So it's also a positive integer. Or you get 0, or n minus 1 is equal to 0. So if you start with 1, if your positive integer is 1, and then you subtract 1, then you get, oops, you can't see that last line, then n minus 1 is 0. 1 minus 1 is 0. So this lemma, this fact, theorem, whatever you want to call it, is true. I think probably if you thought about it, you would say, yeah, this has to be true, which you could prove also using logic. But it's also not very interesting, right? It doesn't really say anything that's very important. If you subtract 1 from an integer, then, something happens. So that's why it gets called a lemma, because maybe it's useful, but not by itself very interesting. Are there any more questions about what these ideas are, axioms, definitions, theorems, and so on? Okay, so since there aren't any questions, we'll just move on to proofs. So this is what we really need to talk about in this chapter, how to prove things in math. And your book also, there's a little explanation of why a computer science major may also want to know how to prove things. And your book puts it really, really quite nicely. If you want to read this little blurb right at the beginning of the chapter, there's a nice explanation about why you guys, who want to be computer programmers mostly, might still be interested in how to prove things. Okay, so theorems, a lot of them look something like this. For all x1, x2, up through however many things that you're talking about, if this thing is true, then this other thing is true. So this is a very common, a very, very common form of a theorem. For example, this corollary says something about all triangles. It says if a triangle is equilateral, then is equiangular. That's of the same form. And so was the other theorem from geometry, talking about two triangles. So this is like a double quantified, what do we call them? Nested quantifiers. So for all triangles X and all triangles Y, if two sides of the triangle, the two triangles are equal, sorry, not two triangles, two angles. Getting ahead of myself, I guess. For all angles of the triangle. And then an if-then statement. So if you want to prove that this statement, this quantified statement is true, then you have to show that no matter what you plug in, no matter what things you're talking about from your domain of discourse, to use words from the last chapter, then this conditional statement is always true. So you have to show that no matter what you plug in, this is always true. Let me just write that down. But we know something important about conditional propositions. We know that if the hypothesis is false, if the hypothesis is false, then the conditional statement overall is vacuously true. So let's keep that in mind. So if the first part, the P functional proposition, is false, then the conditional proposition is vacuously true. But that has an important consequence because it means we don't have to worry about this theorem or this conditional proposition if the hypothesis is false, because it's going to be vacuously true for free without doing any work. So if we want to, well, actually, I had put a line here. The proposition, if P of x1 through xn, then Q of x1 through xn is vacuously true. We can fill in the blanks if the hypothesis is false. Okay. So this means it doesn't matter if the conditional is false. We don't have to actually prove anything. We instead only have to worry about what happens if the hypothesis is true. And this gets us to what's called a direct proof. For a direct proof, we assume the hypothesis, the first part of the conditional statement, is true. And then we use things like axioms. Make sure I get all of these words. Axioms, definitions, theorems, so the things that we were talking about earlier, combined with things like rules of inference that we've learned about, or just logic in general. Maybe another keyword here. For rules of inference, we're talking about arguments, valid arguments. So we use all of these things that we've learned about, or we're going to learn about, to show that the conclusion, the right side of the conditional statement, is also true. Are there any questions before we go on to an example where we actually prove something? Okay, so if there aren't any questions, let's go to the example where we're actually going to try to prove a statement, prove a theorem for ourselves. And to get started, we're going to keep the ideas familiar and simple. We're going to talk about even and odd integers. And just to be totally concrete and logical, we need to make sure we have a definition for what it means for a number to be even. And here it is. This is the way a mathematician would put it. An integer n is even if there exists an integer k such that n is equal to 2 times k. So this is just another way of saying that n is a multiple of 2, or it's divisible by 2. That's what it means for a number to be even. So these are things like 2. Maybe we'll do this below where there's some extra space. So the number 2 is equal to 2 times 1. The number 4 is equal to 2 times 2. We could continue counting up, 6 is 2 times 3. But this also works for negative numbers, like minus 8 is 2 times minus 4. Or larger numbers, 1024 is equal to 2 times 512. Okay, so hopefully this idea is very familiar to you guys. And then related to even numbers are, of course, the odd integers. And an integer is odd if there exists an integer k such that n is equal to 2k plus 1. So just to think through what that kind of abstract definition means, 1 we know is an odd number, and it's equal to 2 times 0 plus 1. The next odd number is 3. It's 2 times 1 plus 1. 5 is 2 times 2 plus 1. Minus 41 is equal to, and then this one you have to worry about what's positive and what's negative a little bit. Maybe 2 times 21, or minus 21, excuse me. 2 times minus 21 is minus 42, and then you add 1 to get the minus 41. So that's how this definition works. Any questions? Okay, so now that we're super clear about our definition, let's go to our theorem that we're going to prove. Okay, so I want to give a direct proof of the following statement. For all integers m and n, if m is an odd integer and n is even, then m plus n is odd. So remember, a direct proof, that's what we were just talking about, is where we're looking at a statement, an if-then proposition, and we're going to assume that the hypothesis is true, and then we're going to use our other ideas and logic to show that the conclusion Q is true. So we're going to assume, in this case, that m is odd and n is even, and then we're going to use logic and definitions and axioms to prove that m plus n is an odd number, an odd integer. So on this first proof, I'm going to demonstrate how you should write them. So much like learning how to write an essay when you were learning how to write English papers, there's also a general kind of format that you need to follow when you're writing a proof. So maybe I'm going to split my paper in half. And on the left side, we're going to put the actual proof, and over here, I'll put some notes as we go along. The first thing that you should do when you're writing a proof is let your reader know that you're going to prove something. And the usual way to do this is to just write the word proof before you start writing anything else. So proof and then a colon to let the person reading your work know what you're going to do. So write proof. To tell the reader what you're doing. And this is just about organization, really. And then after the word proof, we want to write essentially what we're going to be doing for the rest. So we need to write what we know and then write what we're going to prove. In this case, we're going to assume that m is an odd integer, and that n is even. So next, and this is my my guide essentially to what we're doing, is to write what you're assuming. So write your assumption. And then next, write what you're going to prove, what you're going to show is true. And that's the conclusion of the conditional. So we need to show that m plus n is odd. So write what you assume, and then write what you need to show. And then once you have all of your ideas written down, you can start working through the definitions of all of your terms. So work through what the definitions really mean. So in this case, m is odd, so we need to write down what odd means for the number m. And what I mean is something like this. Since m is odd, we go back to the definition that says that there is an integer k such that 2k, m is equal to 2k plus 1. And I'm going to use k1 since I'm going to need to eventually talk about more than one integer. So giving it an extra subscript lets me talk about more than one thing. So m is equal to 2k1 plus 1. We also know that n is even. Let's write that out. Since n is even, you can flip back to the definition. It says there is an integer, and this integer is probably different than the one for m. It's probably different than k1. So let's call it k2, such that n is equal to 2k2, and then we could just stop there since it's even. Okay. So we wrote out what we're assuming, what we need to show. We worked through both definitions for odd and even. So our next step should actually be to complete the proof, to use logic and arguments and that sort of thing, to show that m plus n is odd. So what I need to do now to finish off is just add the two numbers. So maybe I'll work here in the middle, since I'm going to be doing some scratch work, essentially, as part of my explanation. M plus n, I can plug in these other things. M is equal to 2k plus 1, 2k1 plus 1, excuse me. n is equal to 2k2. And I want to continue working on the next line. And since I know where I need to get to, I need to write n plus 1 as 2 times an integer plus 1. That means I want to collect all of these even pieces, let's call them, all these multiples of 2 into a group. So this is starting to look a little bit better. I have multiples of 2 plus 1, but I want to collect this into a single integer times 2. So I'll factor out 2. Like this. And now we're pretty much done. We just have to write our conclusion. Which is perfect since we're right at the end of class. So now we know that m plus n is equal to this. So I'll say something like, since m plus n is equal to 2 times k1 plus k2 in parentheses plus 1, then we know that m plus n is equal to 2 times an integer plus 1. So you could write a little bit more, or you could just say, then m plus n is odd. Let's just keep it brief. Because now it matches with the definition. So we showed that there is an integer where we get something of this form. 2 times an integer plus 1. Okay, so there's a question in the comments about whether a proof will always have the same sequence, or if there's going to be more than one way to format a proof. The answer is there are usually many ways to write a proof, but when you're learning how to write proofs, like you guys are in class right now, I'm going to want you to follow this format pretty much all the time when you're doing a direct proof. So you're going to want to follow these same steps when you're writing a direct proof. We're also going to learn a few other ways to prove statements. Next time we're going to talk about counterexamples, and then we're going to talk about something called induction. And those are going to be different ways to prove things, and their formats will look a little bit different. But most of the time it'll look like this. So if there aren't any other questions, we'll just stop there for today.